Welcome back, Focus Learners. Today, we're diving straight into a brand new explainer, and we're tackling Chapter 7 of our source material, functions. If you've been writing Python code and starting to feel like your programs are getting, well, a little unwieldy, you are in exactly the right place. Today, we're going to master modular Python. We're looking at functions, which are without a doubt the ultimate tool for organizing, simplifying, and truly scaling your code. So, think about your recent projects for a second. What actually happens when your code gets just way too bulky to read? You know the feeling, right? You start scrolling endlessly, you completely lose track of where one calculation ends and another begins. And finding a simple bug, it feels like searching for a needle in a digital haystack. Okay, let's dive into this. I want to ground today's explainer with this really brilliant quote from computer scientist R. Tarjan. He noted, once you succeed in writing the programs for these complicated algorithms, they usually run extremely fast. The computer doesn't need to understand the algorithm, its task is only to run the programs. This hits on a fundamental truth of computer science. Our primary job as programmers is to write clean, modular, and logical algorithms. The computer, it'll do the heavy lifting of executing them. If our logic is a mess, the computer just runs messy code. But if our logic is beautifully structured, everything runs smoother. Here's our quick roadmap for this explainer. First, why we need functions, then the anatomy of functions, giving and getting values, the flow of execution, variable scope explained, and finally, the Python standard library. Let's get to it. Section 1. Why we need functions, solving the bulky code problem. Imagine a company that manufactures tents. If you try to calculate the area, the cost, and an 18% tax sequentially, line by line, you end up with this massive, messy block of code. The absolute best solution to this giant wall of text is modular programming. By definition, this is the process of dividing a computer program into separate, independent blocks of code, or subproblems, with different names and specific functionalities. So instead of one giant script, you create a dedicated block just for calculating the area, another for calculating the cost, and a completely separate one for applying the tax. Just take a look at this comparison. It brilliantly illustrates the point. On the left, a script without functions is a tangled, bulky mess. On the right, using modular programming, the code is divided into highly organized, reusable blocks. Think about it. If the company suddenly decides to sell a totally different shape of tent, but keep the exact same tax calculation, this modular approach allows the programmer to just reuse the tax calculation block without rewriting a single line of that specific logic. It's a real game changer. Section 2. The anatomy of functions. Building the blocks. Now that we understand the why, let's transition right into the how and see how we actually build these blocks in Python. So what is a function? Well, it's defined as a named group of instructions that accomplish a specific task when it's invoked or called. The real power here is reusability. You write the instructions once, you give them a name, and then you can call that name repeatedly from anywhere in your program. You are essentially creating your very own custom Python commands. Now, to make these custom commands truly flexible, we need to pass data into them. And this brings us to a really critical distinction that trips up a lot of new programmers: arguments versus parameters. An argument is the actual tangible value you pass to the function when you call it, like the number 5. A parameter, on the other hand, is the variable defined in the function header that acts as a placeholder to receive that value. And here's a fascinating tidbit from the chapter. If you use Python's built-in ID function, it actually proves that the argument and the parameter refer to the exact same object in the computer's memory. They aren't copies, they're literally two names pointing to the exact same data. Now, Python also lets you set default values for your parameters, which honestly is incredibly handy. But there is a crucial syntax rule you absolutely must follow to avoid instant errors. Default parameter values must always be placed at the very end of the function header. So, if you have a parameter that requires a user to pass an argument, it has to come before any parameters that already have a default built in. Section 3. Giving and getting values. Moving data in and out. Once we know how to define these parameters, we really need to understand how the data actually moves around.
So the crucial point here is that functions don't all communicate the results the exact same way. We essentially have two main categories. Void functions perform a calculation or display a result, like, say, printing a welcome message to the screen, but they don't return any usable data back to the main program. Returning functions, on the other hand, send specific values back to the calling function using the return statement. This means your main program can actually capture that output and use it for the very next step of your calculation.
And here's a really neat feature that makes Python a huge favorite among developers. What if you need to send back more than one result? Say you're calculating both the area and the perimeter of a rectangle. Python functions can easily return multiple values all at once. It does this automatically by packaging them into a tuple. You just write return area perimeter, and Python safely bundles them right up and sends them back to the caller. So simple.
Section 4, the flow of execution, tracing the map. Because we're jumping around now, you can't just read your scripts top to bottom anymore. You have to trace them like a map.
Let's trace this map and see how this builds a four-step lifecycle. Step 1. The Python interpreter encounters the function definition. Now, it doesn't run the code yet, it just makes a mental note that this custom command now exists. The statements inside just wait patiently. Step 2. Somewhere later in the script, the interpreter encounters the function call. Step 3. The flow of control literally jumps from the current line up to the executed function and runs the code inside. Step 4, once it's finished, control returns right back down to the exact point of the call to continue the rest of the program. Tracing this cycle highlights a golden rule of Python. A function must always be defined before it's called. No exceptions.
Section 5. Variable scope explained. Where does your data live? As this flow of control jumps around, we have to manage the boundaries of our data.
Scope is basically the concept that dictates the specific part of your program where a given variable is actually accessible and modifiable. If you try to use a variable outside of its scope, Python's going to throw an error, claiming the variable doesn't even exist.
We've got two main categories of scope to worry about right now. A global variable is like the sun on the left. It's out in the open and accessible anywhere in your code. A local variable, however, is like the sun on the right, locked securely inside a specific function bubble. It exists only while that specific function is active. The second the function finishes its job and returns control to the main program, poof, the local variable is destroyed to free up memory. You absolutely cannot access a local variable from the outside.
Section 6, the Python standard library, using pre-built tools. Writing your own functions is incredibly powerful, for sure, but you don't always have to reinvent the wheel.
You see, Python comes heavily equipped right out of the box with built-in modules. These are basically files totally filled with pre-written functions. A perfect example of this is the math module. By simply typing the statement import math at the very top of your script, you instantly unlock access to a ton of powerful mathematical functions. For example, you can use math.ceil to round up, math.floor to round down, or math.fabs to get an absolute value. You didn't have to write the logic for any of these, you just get to reap the benefits of modularity. Now, what's really interesting about this slide is how it ties everything together. Let's rapidly summarize. Modularity breaks complex problems down into manageable blocks. We pass values into our functions by sending arguments into parameters. We use return statements to send data back. And Python gracefully handles multiple returns using tuples. We have to remember that our script is no longer read strictly top to bottom. The flow of execution jumps to functions and then returns. And finally, scope determines if a variable is local and temporary or global and persistent.
Adopting this architectural mindset? That's exactly what separates a beginner from a truly proficient programmer. So I'll leave you with this question to chew on. How will modular programming change the way you design your next complex application? The next time you find yourself copying and pasting the exact same lines of code, pause, define a function, and let the computer do the heavy lifting for you. Thanks for joining me on this explainer, and keep your learning focused.